interjects.
Happy birthday to you. Happy birthday to you.
I hear it.
Happy birthday, dear Lindsay. Happy birthday to you.
Woo-hoo. That's why. Still got me? All right, I think we're good. All right, so if you're watching this at home because you have nothing better to do, we were talking about the Suburban takes up too much space and the car has to share a smaller space, and that's an example of a polar relationship where they share, but they share unequally. All right, let's do this. I believe we need to finish our notes on bonds. We're going to have a pretty busy day, which I know you're excited about, because who wouldn't be? Don't answer that. All right, I don't know exactly where we were. Can you help me out? All right, we didn't do anything with nonpolar? You have a word, though. Oh. All right, so nonpolar, everything we learned about polar, these are nonpolar. So if a polar does not share equally, then we would probably assume that a polar does what? Shares more equally. All right, and this would be like two twins sharing a car. You would hope they would be more equal because one's not really older than the other, even though I know they are by like 30 seconds. But
if they're identical twins, how do you know who's who and who has which car?
See, that's what I'm saying. My nieces are twins. Maybe I could. Well, they don't drive. They're 17 and they don't have their driver's license. Well, I don't hate them. The problem is they live in a small town, and it's not really a problem, but here's their house, here's their school, and here's their church. They're all within like a block and a half. Probably 70 miles away. I was just there this weekend, and there's nothing. What's that? They have the famous Red Onion Al and Barb's Diner or something like that. It's pretty good, and they have a Mexican place that's fantastic. And then you can go out their back door and shoot squirrels and eat them. Their backyard's pretty amazing. They actually like live right at the bottom of a cliff, and you can hike up. Like, it's a pretty cool place. Go ahead. What was that noise? All right, bonds with electronegativity differences between the atoms that are less than 0.6 are nonpolar bonds. So you can see the word small written with an arrow. What we're saying is if no one's bigger or more electronegative, then neither one of them will pull the electron towards it. They share it more evenly, and thus they are nonpolar. Remember, polar means two sides, right? So nonpolar means non-two-sided. It's a neutral molecule pretty much all the way around. Because this difference is so small, the electron attractive forces of each atom are almost equal. This isn't working very well. This results in a molecule with a relatively neutral charge. So we have an ionic bond where each individual piece has lost and gained electrons to become a positive and a negative ion. We have a polar bond where electrons are moved to one side but not completely removed. And then we have a nonpolar where the electrons are pretty much equal everywhere. Yes, post. That is just measured in a lab. You can get an electron around it, and if you know its mass and its acceleration towards the nucleus, you can measure that pretty easily. Now, you have to have some really fancy tools, but it's not too hard to figure out based on how fast it moves in. Good question. All right, now, we're already past nonpolar. Nonpolar are super boring. They don't really do a whole lot. The one thing we do need to do in the picture with the 5 little spheres, in the middle one where you put a C, and then around it where you put H's. So what do you think the formula of that is? It's right there in front of you. CH4. If we do the math for CH4, it's 2.5 and 2.1, so the difference is 0.4. So that means it would be a nonpolar substance, and it is. It's called methane. It's natural gas. It's what heated your shower water this morning. Most likely, it's what we've been burning. No question, right, Raquel? Okay, just a stretch. All right, in a metallic bond, metallic bonds are best explained by going to church. Now, if you haven't ever gone to church, I'm not judging you. I'm just using it as an example. So here we go. In a pure metal, the valence electrons are free-floating among closely packed, positively charged ions. And I'll make this make sense with church here in a second. All right? Remember, metals want to be losers, right? But if they're just all together, there's no one to take their electrons. So it's hard to be a loser if there's no one to take them. So they have to get creative, and that's what a metal will do. All right, the sea of floating electrons are what gives metals their physical properties. Now, this is the matching term. If you can tie the word sea to a metallic bond, you'll do well on that test question. Because if you've had, well, you all have had chemistry, not just me, but every test has a matching section. The matching section on this test is all about bonds. So a metallic bond, a sea of free-floating electrons. All right? Whoops. Okay, so what does this have to do with church? All right, well, if you've ever, how about this? Every church I've ever gone to, there's a bunch of people in a meeting, and there's tons of moms and dads and kids. And have you ever been at one of those meetings and there was just a kid that just was walking around everywhere? Raise your hands if you've ever seen that. 2 or 3 of them sometimes just randomly walking around wherever they want. And it's kind of strange if you really think about it, because in society you don't usually just let your kids walk around freely amongst other people, unless you're rude, but whatevs. All right, but the deal is, like in a metallic bond, those electrons can go where they want so that no one and everyone at the same time takes care of all the electrons. It's kind of the same reason why that overstressed mom lets that kid walk around wherever they want, because everyone in that room is taking care of the kid at the same time. And at the same time, no one is taking care of that kid. Can you understand that? It's kind of weird. It's like crowdsourcing. You get a free hour of babysitting because every single person at the same time is looking out for that kid, but they don't belong specifically anywhere. And if the kid falls, you have like 20 moms that are like, oh, and 20 dads that are like, good, now go sit where you belong. Because men are butt faces, in case you didn't know. But it's really very similar. In the metal, these electrons, they sort of belong here, but they can sort of go wherever they feel like. And it's fine because no metals really wanted them. But at the same time, it's a game of musical chairs where the music never stops. If the music doesn't stop, do we care how many chairs are set up? No, it never, ever matters. So in this, every metal has too many electrons or too little at any point in time, but we don't care because we never stop the music. Now, this is what gives metals their interesting properties. If I add even one electron to this system, it will repel a lot of electrons, and at least one electron will pop off the other side. And what do we call it when electrons flow through things? Electricity. And metals are the only things that consistently will conduct electricity. That's because their electrons are free to move. They're not specifically tied to a nucleus. They're just kind of all kicked out, like the family party. All the kids go outside and whatever. If they come back in, life's all right. If they don't, that's fine too. All right. We okay with that? Super fascinating lecture, I can tell. You're welcome. All right, let's move on to hydrogen bonds. really loud. All right, the first thing you should know about a hydrogen bond is it's actually not even a bond, which is kind of dumb because it's called a hydrogen bond. But really, it's an attractive force, and that's your matching term as well. A hydrogen bond is an attractive force, meaning there is no sharing, losing, gaining, or anything of electrons. There's a positive thing that's attracted to a negative thing, and they sort of hang out. Like your dryer sheet. Who has ever gone to school, felt something weird in your pant leg, and pulled out a dryer sheet? Is it just me? Okay, there's two. Or a sock. Who said sock? Yeah, you're like, what? Oh, yeah, it happens to me at least once every 10 years. So all the time, all right? This is weird, and maybe Brecklin can back me up here, but you probably haven't. But when you clean up after a track meet in the wintertime, there's always dryer sheets. There's always dryer sheets on the ground. Like, why would there be dryer sheets? Well, it's because it's freezing cold, and there's 10,000 people with 10,000 blankets that they just dried the night before, and the dryer sheet stuck to the blanket. Who's had a dryer sheet stuck to something in their life? All right. How hard was it to pull off? Not hard at all. But it was attracted to the blanket, just like hydrogen bonds are. They're sort of attracted, so there's a thing there, but it's not that strong. You with me? A normal bond would be like trying to pull your blanket apart. That's a lot harder than just pulling the dryer sheet off. Are we all right with that? Okay. Next track meet, look for dryer sheets. I promise they're there somewhere. All right. So the explanation here, it's called a hydrogen bond because it most often happens with hydrogen. They are attractive forces in which hydrogen that is covalently bonded to a very electronegative atom is also weakly bonded to an unshared electron pair. That's a really confusing way of saying that we have hydrogen bonding in water. So what will happen? We know water's polar or has two halves, correct? The top part of it is negative, leaving the bottom part of it positive. That's why we call it polar. Well, if there's another water molecule around, tell your lab partner how you think that water molecule would line up with that water molecule if they were to hang out. Ready, set, go. Hope he's a nice kid. All right, if we had another water particle, hopefully you and your lab partner figured out that the H would be here and the O would be away. Who had it something like that? Or you could have put the O here and the H's. We all right with that? This attraction is called a hydrogen bond. Not a bond, more like the dryer sheet, but anyway. When you get a lot of them, they line up and make some sort of lattice structure. If we get a lot, you end up with that. Let me get some of these out of the way. Yeah, this would just be a chunk of ice, essentially, if it was a solid. All right? Water is extremely ordered in the way that it lines up because of hydrogen bonding. In biology, you probably learned water was polar, and you probably learned water had hydrogen bonding, and that's why, like, the Jesus bug can walk on water. You guys ever, did they teach it that way? Well, that's what they call them. We call them skeeters growing up, but it's a bug that takes advantage that, no one's ever heard them called a Jesus bug? Raise your hands if you've heard that before. Thank you. 1, 2. Maybe we're weird. I think we're normal, and everyone else is weird. But they take advantage of the fact that water is attracted to itself. Just looking right here, you've never thought about it once. But just the fact that water comes out in a stream proves that that's polar. It sticks together, and I could even bend this stream a little because it all sticks together. I get it to come onto my finger, and then I can move it just a little bit. Who's ever done that before? That's because water is attracted to itself. Go ahead. How big? It's like 3 angstroms. It's this big. It's .0000000000003. No, it'd be like a super, super fine mist. Like you're actually breathing in water right now that you can't see, but it's water vapor. But yeah, it would be an extremely fine mist all the time. Now, has anyone ever had the crappy experience of trying to pour paint thinner out of a metal can? Anyone? You take that metal square and you're like, oh, I'm just going to pour it in there. And you know how liquids pour. They go like that. But the problem with paint thinner, you tip it and it keeps onto the can and falls off the bottom corner. Who's had that? At least 1, 2, 3, 4, 5, 6, 7. It's the most annoying thing on the planet. Because you also know at the same time that paint thinner could explode. Could kill you. It's toxic. Whatever. It comes in a metal can. It must be dangerous. And then you go to pour it and it goes everywhere, all over here. Well, the reason why is because your paint thinner does not have hydrogen bonding. There's nothing in the liquid of paint thinner to make it stick to itself. In fact, it's more attracted to the metal can that it's in. So when you pour it, it'll stick to the metal and drip off the bottom. So the only way to pour it is to quickly go from here to straight up so it only can fall right out. There's no advantage there. Or attraction there. We're pretty much done. I think that's the last slide, isn't it? Okay. Whew. We're about a third of the way done with what we need to do today. Let me pause. All right, so this is page 10. The first thing, let me borrow. Thank you. The first thing you're going to do, so it says water, and then it shows you its structure. So you're going to write the names and then draw the structure in the column next to it. Easy enough? Now, these pictures get super complicated, and I've done this for 15 years, and I've heard pretty much every complaint possible. So feel free to complain, but just know I'm not going to listen. So draw that real quick, and then we'll move to the next one. So we got water. It's H2O. Now we have hexane. Hex is a prefix for 6. So if it has hex at the start, it means 6 carbons. All right, now you don't have to know it for this class at all, but this is a pretty cool thing, and if you go into medicine at all, you'll take a thing called organic chemistry, and you'll learn a whole new language on what this part means and what this part means. If you were in biology ever, you learned about saturated and unsaturated things, mostly fats. Every ane is a saturated substance, meaning there are no double bonds at all. Okay, next. Well, actually, some people are still writing. Where? Okay. Now, the next one, I believe I didn't write the name on. So first off, the name of the thing is salt. And then NaCl is its structure. Well, you'll have to copy from your lab partner. Yep. I know. Well, structures of things that are ionic are really boring. Nope, nope, nope. Neither's that one. It's polar, but it has hydrogen bonding, which is an attraction, remember. Okay, next is the worst one. It's called naphthalene. This is the component in mothballs. So if you've ever gone to your grandma's house, it was like, man, it smells like old people in here. You were most likely smelling naphthalene, because they have clothes made out of natural materials, and moths will eat that. Most of our clothes are fake. And these drawings don't have to be perfect. Speaking of, where's our artist? Yeah. Yeah. It's not that bad. Put 2 in the middle and then make pentagons around them. I guess they are hexagons. Oh, hey, what's up? All right, we ready to move to the next one? Oh, sorry, we're checking my email. There we go. Pentanol is what this is called. Penta means 5 oxygens, 5 carbons. Nol, that's your thing when you have an OH on the end. She's a doll. It's my baby girl. All right, next up, they're all easy from here on. We have methanol. What does the all mean at the end again? All right, that the substance ends with an OH. All the alcohols that you've ever heard of, they are alls, alcohol. Methanol, ethanol, that's the alcohol that people can drink. Pentanol, isopropyl alcohol, that's rubbing alcohol. So that's propanol essentially. They all have an OH at the end. Meth, everyone's like, what the? But meth, that is just a prefix that means you have this thing as part of your molecule. Because meth isn't just meth. Meth is methamphetamine. And what that would be is at least something in the structure of that drug has that functional group of C and 3 H's. In case you care, because people ask all the time. All right, copper 2 sulfate. All right, we ready? Then iron, pretty simple. And then copper. There doesn't need to be 3. There could be a million of them, and there could be 2 of them. It doesn't really matter. It's just a chunk of metal. All right, your next job for the next 3 or 4 minutes is to figure out the type of bonds for each one of these. Now, I need to clarify just a couple because they can be tricky. So water's easy. It's O and H's that you're going to look. Hexane is easy. CH's, NaCl's easy. Naphthalene, easy. Pentanol has an O. Ignore the O in pentanol. But that will be annoying because in methanol, you do care about the O. So for methanol, circle the CO, and when you do your math, do it for C and O. And you know what I mean by math? You're finding your electronegativity difference. What's carbon, what's oxygen, and then finding that on your chart. Copper 2 sulfate, I'm going to tell you, is ionic. Then the last two are chunks of metal. What's our name for metals? Metallic bonds. So just take a minute and do those. If you don't remember how, ask your lab partner. If you both don't remember, raise your hand and we'll come fix you. So go ahead and determine the types of bonds on that page 10. All right, so water is what? Polar. You can pass your bio class now. What was hexane? Nonpolar. What is NaCl? Ionic. Naphthalene. Nonpolar. It's a bunch of CHs, but it's still just C's and H's. Pentanol. Nonpolar. Methanol is where I switched it up. So what was that one? That should be polar because you find C and O and the difference is a 1. All right, and the reason why in this one we care about the O, but in the other one we didn't, is because the other one was so much bigger over here that the O was kind of just a little piece. But in methanol, the O is very dominant, and so was the H. So it's polar. Okay, next up was copper 2 sulfate. I told you that one, and that one. All right, so what we're going to do now, and please write from the top across because I'm going to lower it here in a minute. We're going to fill out this gigantic data table. So these are the properties of these things that we usually find in the lab, but I just don't do anymore. So fill that out and we'll scroll up in a minute. All right, now you and your lab partners looking at this table, I want you to see if you can answer these 3 questions. And just do it, pretend that page 11 is sideways and just write somewhere on there the answer to these 3 questions. So use your table, look at these 3 questions, search. One of them is a lot harder than the other 2 to answer, and just see if you can figure these out real quick. Sort of no and sort of yes. Did anyone notice it's kind of weird? All right. All right. Did anyone hear that? I'll repeat it for the video. If you put salt in water, the solution will conduct, but just a piece of salt won't conduct. So in your data, it should have shown you that ionic things did not conduct, but when they were put into water, that solution conducted. Did you notice that? So the answer, like technically, do ionic bonds conduct electricity? The answer is no, which is what most of you put them down. And then you could have put unless in solution. All right, now, do polar bonds dissolve in nonpolar liquids? Almost everyone had this right. What's the answer? No, they do not. But polar things dissolve in polar things. Did you notice that? And nonpolar things, what do they dissolve in? In nonpolar things. And if you'll look at the bottom of that page, it tells you, like normal looking, this is called likes dissolves likes data table. And why it's called that is because in here we learn that things with like bonds dissolve things with like bonds. And that's why a permanent marker can be erased. You just have to have something that is like bonded. So a permanent marker is a nonpolar substance. So to wash it off, you need a nonpolar substance. But usually in our world, what do we wash things with? Water, which is polar, and that makes the marker permanent. You all right with that? Okay. Are ionic bonds brittle? That one should be the easiest. Yes, they are. All right. This is an example of the type of stuff you have to do on your exam. But we make it a lot easier by giving you this information from the data table on your periodic table. So everyone turn here, and we'll run out of time before we finish, but we'll fill out as much as we can of this table right here so that we're ready for our exam. Summarizing it and writing it on the right side of that so that you all see. We've been using this for just a little while already, the greater than 1.7, the numbers here. But now we're going to put things here. So first thing first, solubility means, does the thing dissolve? So if you don't know that word, that's fine, right? Does it dissolve? That's what solubility means. Do ionic bonds dissolve from our data? In water, so I'm going to put water, but I want you to write something besides water also. I want you to write that they dissolve in water/polar liquids. The reason why I'm doing that, and it's redundant to someone that really gets chemistry, like, why are you writing both? Well, you're high schoolers. And on the test, I might ask, does it dissolve in water? Or I might ask, does it dissolve in a polar substance? And that's redundant, but put it there anyway. So you don't have to think, you just have to answer. All right, conductivity. We just said, do ionic bonds conduct? No, but they do when? In solution. So right here, put only in solution. Because the test question will ask you, does it conduct in pure form? And the answer would be no. It will also ask you, will it conduct in solution? And the answer will be yes. All right, malleability. We're either going to put malleable or brittle. What are these? Brittle. And then MP and BP, that's the melting and boiling point. And ionic bonds have a high melting and boiling point. All right, polar bonds for solubility is water/polar again. I think the bell rings in 20 seconds, so we'll call it good right there. We'll fill out the rest tomorrow.